February 19th, 1943, 14 miles south of Guadalcanal, Master Sergeant Mike Quirk watches the 6th Jeep tire of the morning disintegrate into smoking rubber fragments. The Willys MB sits motionless on the jungle trail, its right front wheel reduced to shredded carcass and exposed steel belts. The tire had lasted exactly 473 miles, 3 weeks of service. Quirk runs his hand over the remains, feeling the characteristic cracks that spread like spiderwebs across what used to be the sidewall. The rubber is hard, brittle, nothing like the supple compound that left the Goodyear factory in Akron 8 months ago. Around him, the jungle breathes its humid poison, 92 degrees, 87% humidity, and enough ozone from tropical thunderstorms to crack rubber faster than enemy bullets could puncture it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from wherein the world you are watching from today. The Marine Corps has 340 Jeeps scattered across the Solomon Islands. By Quirk's calculation, based on failure reports flooding into the motor pool, they're losing tires at a rate that will ground the entire fleet within 6 weeks. Every replacement tire shipped from the States arrives with the same vulnerability, the same chemical weakness that makes it food for the jungle itself. 12,000 miles. That's what the engineers promised. That's what the specification sheets guaranteed. 12,000 miles of service life from each 6.00 by 16 tire. On the proving grounds in Michigan, on the test tracks in Ohio, the tires delivered exactly what the data predicted. But Michigan doesn't have 100-degree heat combined with moisture so thick you can taste it. Ohio doesn't generate atmospheric ozone that attacks double bonds in rubber molecules like acid through cloth. Quirk tosses the ruined tire onto a pile of identical casualties. Somewhere in Connecticut or New Jersey, in laboratories with climate control and precise measurements, chemists are presumably working on this problem. But the Marines on Guadalcanal are dying now, not from Japanese fire alone, but from immobility, from supply lines that collapse when the vehicles meant to maintain them sit disabled with destroyed tires. What Quirk doesn't know, what none of the mechanics scattered across the Pacific Theater understand, is that the problem isn't simple material failure, it's chemistry. Specifically, it's the unstable carbon-carbon double bonds in natural rubber that make the material both wonderfully elastic and fatally vulnerable. And somewhere in the basement laboratories of the Firestone Tire and Rubber Company, a 31-year-old chemist named Bill Larson is staring at test results that everyone else has dismissed as laboratory error. The crisis began on December 8, 1941. 24 hours after Pearl Harbor, Japanese forces captured Singapore, the center of global natural rubber production. In a single coordinated strike, the Empire of Japan seized control of 90% of the natural rubber supply that fed American industry. For the automotive manufacturers of Detroit, this was an inconvenience. For the United States military, preparing to fight a two-ocean war with equipment that consumed rubber in quantities measured by the ton, it was catastrophic. Natural rubber comes from Hevea brasiliensis trees, cultivated in vast plantations across British Malaya, the Dutch East Indies, and French Indochina. The latex these trees produce forms the foundation of everything from bomber tires to gas masks, from tank treads to the insulation on miles of electrical wiring inside every warship. In 1941, the United States imported $168 million worth of natural rubber annually. By February 1942, that supply chain simply ceased to exist. President Roosevelt understood the magnitude of the crisis. He created the Rubber Reserve Company and appointed Bernard Baruch, James Conant, and Carl Compton to lead an emergency committee that would either solve America's rubber problem or watch the war effort collapse under its own weight. The committee's conclusion was unambiguous. America needed to produce 1 million tons of synthetic rubber annually within 2 years, or lose the war. The chemistry of synthetic rubber was not new. German scientists at IG Farben had developed Buna S in 1929, a copolymer of butadiene and styrene that could substitute for natural rubber in many applications. American companies had experimented with similar formulations, but none had achieved the combination of properties necessary for large-scale tire production. Synthetic rubber was too stiff, too temperature-sensitive, too prone to catastrophic failure under conditions that natural rubber handled effortlessly. On March 26, 1942, representatives from Firestone, Goodyear, B.F. Goodrich, and United States Rubber Company gathered with government officials to agree on a mutual recipe for what would become known as GRS, Government Rubber Styrene. The formula was deceptively simple: 75% butadiene, 25% styrene, potassium persulfate as catalyst, soap as emulsifier, water and dodecyl mercaptan as modifier. Mix, polymerize, coagulate, and dry into bales that looked almost identical to natural rubber. But looking identical and performing identically were separated by a chasm of chemical complexity that nobody fully understood in early 1942. The first tires produced from GRS rubber were spectacular failures. They hardened in cold weather, softened in heat, and wore out 3 times faster than natural rubber on any surface more abrasive than smooth concrete. The polymer chains were too short, the cross-linking too aggressive, the carbon, black reinforcement insufficient to prevent the rapid degradation that occurred whenever stress met temperature. Bill Larson joined Firestone's research division in October 1941 with a Ph.D. in organic chemistry from the University of Illinois and absolutely no practical experience in rubber compounding. His dissertation had focused on oxidation mechanisms in unsaturated hydrocarbons, an esoteric subject that seemed to have limited application to industrial production. But by March 1942, that esoteric knowledge suddenly became the most valuable expertise Firestone possessed. The problem, Larson realized as he studied failure reports from military proving grounds, wasn't primarily mechanical. Tires weren't wearing out from abrasion or structural fatigue. They were being chemically destroyed by oxygen, ozone, heat, and humidity, working in combination to attack the molecular structure of the rubber itself. Every double bond in the polymer chain represented a point of vulnerability, a site where oxygen could insert itself and begin the cascade of reactions that led to chain scission, cross-linking, and eventual mechanical failure. Natural rubber is polyisoprene, a polymer with methyl groups attached to every other carbon atom along the double-bonded backbone. This structure gives natural rubber its excellent elasticity, but also makes it extraordinarily susceptible to oxidative degradation. In the cool, dry climate of Michigan's proving grounds, natural rubber tires could indeed deliver 12,000 miles of service. But in the hot, humid, ozone-rich atmosphere of the South Pacific, those same tires began destroying themselves the moment they rolled off the cargo ships. Larson's first insight came from analyzing the pattern of failure. Tires weren't failing uniformly. They developed cracks perpendicular to the direction of stress, characteristic of ozone attack. The cracks appeared first on the sidewalls, where rubber stretched under load, but received minimal abrasion from contact with the road surface. This was chemical degradation, pure and simple. Ozone molecules in the atmosphere were reacting with the double bonds in the rubber, cleaving the polymer chains and creating the deep fissures that eventually propagated into catastrophic structural failure. The solution was theoretically simple. Add antiozonants, chemicals that preferentially react with ozone before it can attack the rubber. These compounds had been known since World War I, when French chemist Charles Moreau discovered them while working on chemical warfare agents. But knowing antiozonants existed and formulating them into a rubber compound that could survive tropical conditions while maintaining flexibility, strength, and durability represented entirely different challenges. Larson began his experiments in April 1942, working with a class of compounds called aromatic amines. These molecules contained benzene rings with attached nitrogen, groups, structures that reacted readily with ozone, and formed stable oxidation products. The trick was finding an aromatic amine that remained mobile enough within the rubber matrix to migrate to the surface where ozone attack occurred, but not so mobile that it simply sweated out of the compound during storage or use. His supervisor, Dr. Robert Hammond, was skeptical. Hammond had spent 20 years in rubber compounding and understood the complexity of balancing competing properties. Every additive you put in changes everything else, Hammond explained during one of their weekly review meetings. Add your ozone protection, and the compound becomes too soft. Add more sulfur to compensate, and it becomes too brittle. Add plasticizers to restore flexibility, and you lose tensile strength. The polymer matrix is an equation with 12 variables, and every time you change one, the solution collapses. But Larsen had an advantage that Hammond's experience couldn't match. He understood the fundamental chemistry at the molecular level. He could predict how different aromatic amines would behave based on their electronic structure, their molecular weight, their polarity. This wasn't trial and error mixing, it was rational design based on first principles. By June 1942, Larsen had synthesized 43 different aromatic amine derivatives and tested each one in accelerated aging chambers that simulated tropical conditions. Temperature, humidity, and ozone concentration all elevated to levels that would destroy conventional rubber within 72 hours. Most of his compounds failed. The amines either reacted too slowly to provide protection, or they migrated so rapidly that the rubber surface became greasy and lost all friction. Compound number 37 was different. N-isopropyl N-in, phenyl-phenylane diamine, a mouthful of chemical nomenclature that described a molecule with a benzene ring flanked by nitrogen atoms carrying both phenyl and isopropyl groups. This particular arrangement created a compound that migrated through rubber at exactly the right rate, reactive enough to intercept ozone, but stable enough to remain effective for months of exposure. Test samples incorporating compound 37 survived 500 hours in the aging chamber with minimal cracking. By comparison, control samples without the additive showed extensive surface degradation within 72 hours. Larsen's data suggested that tires formulated with this aromatic amine could extend service life in tropical conditions from 500 miles to something approaching the original 12,000-mile specification. But laboratory success and production reality existed in separate universes. Compound 37 required a multi-step synthesis, starting from aniline and isopropyl bromide, producing a product that cost $17 per pound when produced in small batches. Firestone would need thousands of pounds to treat even a fraction of their tire production. At $17 per pound, the cost became prohibitive for military specifications. Hammond delivered this information with the satisfaction of a man whose skepticism had been validated. Beautiful chemistry, he acknowledged, examining Larsen's lab notebook. Completely impractical for production. You've proven the concept, which is valuable. Now we need to find something cheaper, something we can make in tank car quantities, or your breakthrough stays in the laboratory. Larsen closed the notebook, his breakthrough reduced to an academic curiosity by the brutal economics of industrial chemistry. But he wasn't ready to abandon the approach. Somewhere between his elegant but expensive synthesis and the cheap but ineffective compounds already in use, there had to be a formulation that worked both chemically and economically. What Larsen didn't know, as he filed his lab notebook in July 1942, was that the answer was already sitting in a different Firestone laboratory, classified as a failed experiment from 1938. A simpler aromatic amine that had been dismissed because it caused slight discoloration in white rubber products. But military tires were black, loaded with carbon black for reinforcement. Nobody cared if they discolored. And the synthesis could be accomplished in a single step from commercially available starting materials. Master Sergeant Quirk is still dealing with destroyed tires on Guadalcanal, still watching jeeps sit immobilized while Japanese forces maneuver through terrain the Americans can't access without functional vehicles. The rubber crisis is accelerating, driven by chemistry that the mechanics can't see and the supply officers can't quantify. But in Connecticut, a chemist is about to rediscover an experiment that everyone else had forgotten, and that discovery will change everything about how rubber survives the jungle. The breakthrough came from an unlikely source, not from Larsen's systematic investigation, but from a conversation in the company cafeteria in August 1942. Larsen was reviewing his notes on aromatic amine synthesis when James Keller, a junior chemist from the pigment division, sat down across from him. Still working on the tropical degradation problem? Keller asked, stabbing at a plate of reconstituted eggs that tasted like cardboard even by wartime standards. Dead end, Larsen admitted. The chemistry works perfectly. The economics don't. Keller nodded, chewing thoughtfully. What about 6-ppd? We used it in some trials 4 years ago for pale rubber compounds. Worked great for ozone protection, but it turned the rubber purple. Management killed the project. 6-ppd. None. 3-dimethylbutyl N-phenylphenyldiamine. Larson had seen references to it in the literature, but dismissed it because of the documented discoloration. But Keller was right. Military tires were black, loaded with carbon black for reinforcement, absorbing so much pigment that any discoloration would be completely invisible. You have the synthesis protocol? Larson asked, his cafeteria tray suddenly forgotten. Keller shrugged. Should be in the archives. Project number 43-38. Want me to pull it? Within a week, Larson had synthesized 20 pounds of 6-ppd and formulated it into test batches of GRS rubber at loading levels ranging from 1 to 3 parts per 100 of rubber. The compound was soluble in the rubber matrix, mobile enough to reach surface sites where ozone attack occurred, and chemically aggressive enough to intercept ozone molecules before they could damage the polymer chains. The accelerated aging tests confirmed what Keller's old project had demonstrated. 6-ppd provided exceptional ozone protection, but Larson wanted more than laboratory validation. He wanted field confirmation under the exact conditions where tires were failing. That's where things became complicated. Official channels required extensive testing protocols, committee approvals, procurement authorizations. The military rubber program was coordinated through the Rubber Reserve Company, which answered to the War Production Board, which reported to a dozen different oversight committees. Getting approval for field trials of an unproven compound would take months, and Quirk's jeeps on Guadalcanal didn't have months. Larson made a decision that could have ended his career. He contacted the supply officer at the Army Motor Pool in Fort Benning, Georgia, and explained that Firestone had a batch of experimental tires incorporating improved tropical resistance compounds. Could they arrange for 20 tires to be shipped to the Pacific for unofficial evaluation? No paperwork, no formal testing protocol, just get them into service and report back on performance. The supply officer, a captain named Morrison who understood that regulations mattered less than results, agreed. 20 tires, marked with an inconspicuous code number that linked them back to Larson's formulation, shipped to Guadalcanal in September 1942. Master Sergeant Quirk received the shipment with the skepticism of a mechanic who had watched too many promised solutions fail in practice. But tires were tires, and his jeeps needed them. He mounted 4 of the experimental units on a Willys MB assigned to Lieutenant Colonel Merritt Edson's battalion, vehicles that operated in the worst conditions the jungle could provide. 3 months later, Quirk filed his report. The experimental tires showed minimal degradation, no ozone cracking, no sidewall deterioration, wear patterns consistent with normal abrasion rather than chemical breakdown. By January 1943, those tires had accumulated 4,000 miles in conditions that destroyed conventional tires in under 600 miles. Larson received Quirk's report through unofficial channels in February 1943. The data was crude, lacking the precision of controlled laboratory testing, but the conclusion was unmistakable. 6-ppd worked. In actual jungle conditions, under actual combat loads, with actual Marines depending on the vehicles, the formulation delivered exactly what the military needed. Now came the challenge of converting unauthorized field trials into official production. Larson presented his data to Hammond, who presented it to Firestone's technical committee, who presented it to the Rubber Reserve Company's oversight board. The response was immediate and overwhelming. If Firestone could produce 6-ppd in quantity and formulate it into tires without compromising other performance characteristics, the military would purchase every unit the company could manufacture. Production scaling began in March 1943. The synthesis was straightforward enough, but producing thousands of pounds per month required dedicated equipment, trained operators, and quality control, protocols that didn't exist. Firestone built new reaction vessels, trained new technicians, and established testing procedures that ensured every batch met the specifications Larson had defined. By May 1943, Tires incorporating 6 ppd were rolling off Firestone's production lines at a rate of 50,000 units per month. They shipped to every Pacific theater operation, from Guadalcanal to New Guinea, from the Philippines to the Marshall Islands, and they performed exactly as Larsen had predicted. Service life in tropical conditions extended from 600 miles to over 12,000 miles. Jeeps that had been sitting disabled for lack of functional tires suddenly regained mobility. Supply lines that had collapsed under logistical strain suddenly functioned with new efficiency. The chemical explanation was elegant in its simplicity. 6 ppd molecules migrated through the rubber matrix to surface sites where ozone attack occurred. When ozone molecules encountered the treated surface, they reacted preferentially with the aromatic amine rather than with the polymer chains. This sacrificial protection allowed the bulk rubber to maintain its structural integrity while the anti-ozonant slowly depleted through oxidation. But 6 ppd was only part of the solution. The second critical breakthrough came from understanding carbon black, the reinforcing agent that had made black tires standard since the early 1900s. Carbon black particles, produced by incomplete combustion of petroleum or natural gas, provided extraordinary reinforcement when mixed into rubber compounds. A tire without carbon black might last 100 miles. The same tire with properly formulated carbon black could deliver 50,000 miles. The mechanism of carbon black reinforcement remained somewhat mysterious even in 1943. The particles were extraordinarily small, measured in nanometers, with surface areas that reached 300 square meters per gram. When mixed into rubber, these particles created a three-dimensional network that distributed stress throughout the polymer matrix, preventing crack propagation and improving tear resistance by orders of magnitude. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But not all carbon blacks performed identically. Different production methods generated particles with different surface chemistries, different aggregation structures, different reinforcing characteristics. Channel black, produced by burning natural gas in limited oxygen and collecting the soot from ion channels, created small particles with high surface area. Furnace black, produced by pyrolyzing petroleum feedstocks in high-temperature furnaces, generated larger particles with different surface properties. For tropical tire applications, Larsen discovered that a specific type of furnace black designated N330 provided optimal performance. The particle size and surface chemistry of N330 created strong interactions with both natural and synthetic rubber, improving tear strength and abrasion resistance, while maintaining the flexibility necessary for jungle terrain. The combination of 6 ppd for ozone protection and optimized carbon black for mechanical reinforcement transformed synthetic rubber from an emergency substitute into a material that actually exceeded natural rubber's performance, under specific conditions. But Larsen understood that chemical protection and mechanical reinforcement weren't sufficient. The third element required for long-term durability was thermal stability. Rubber degrades through two competing mechanisms when exposed to heat and oxygen. Some polymers undergo cross-linking, forming additional chemical bonds between chains that make the material progressively harder and more brittle. Other polymers undergo chain scission, breaking the long, molecular chains into shorter fragments that make the material softer and weaker. Natural rubber and GRS both predominantly suffered chain scission under oxidative conditions. The solution required antioxidants, compounds that intercepted the free radical reactions responsible for oxidative degradation. These chemicals needed to be stable at elevated temperatures, soluble in rubber, and capable of breaking the chain reaction cascades that propagated thermal damage through the polymer matrix. Phenolic antioxidants had been used in rubber compounding since the 1920s, but most formulations were optimized for natural rubber rather than the newer synthetic materials. Larsen spent considerable time in late 1942 identifying phenolic compounds that provided effective protection in GRS rubber without compromising other properties. His final formulation combined hindered phenols, molecules with bulky chemical groups adjacent to the reactive hydroxyl site, creating compounds that could donate hydrogen atoms to stabilize free radicals without themselves becoming destabilizing radicals. The specific phenol Larsen selected, 2,6-D-tertbutyl-4-methylphenol, offered optimal performance at loading levels of 1 to 2 parts per 100 rubber. By August 1943, Firestone's tropical tire formulation had evolved into a complex chemical system. GRS polymer, 75% butadiene and 25% styrene, N330 carbon black at 50 parts per 100 rubber for reinforcement, 6 ppd at 2 parts per 100 for ozone protection, hindered phenol antioxidant at 1.5 parts per 100 for thermal stability, sulfur cross-linking system with accelerators and activators for vulcanization, plasticizers and processing aids for manufacturability. The final compound contained 37 distinct chemical ingredients, each serving a specific function, each interacting with every other component, through mechanisms that were partially understood at best. But the formulation worked. Field reports from the Pacific confirmed what laboratory testing had predicted. Tires were lasting 12,000 miles in jungle conditions that had destroyed conventional tires in under 600 miles. The impact on military operations was dramatic, but difficult to quantify precisely. Jeeps remained mobile. Supply lines functioned, artillery could be moved, wounded could be evacuated. These weren't headline-grabbing victories, but they were the unglamorous logistics that determined whether armies could function or collapsed under their own weight. Lieutenant Colonel James P. Sullivan, supply officer for the 1st Marine Division, filed a report in November 1943 that captured the operational significance. Improved tire durability has effectively doubled our operational radius. Missions that were previously impossible due to expected vehicle attrition are now routinely successful. The maintenance burden on motor pool personnel has decreased by approximately 60%, freeing mechanics for other critical work. Back in Connecticut, Bill Larsen received these reports with quiet satisfaction. He had solved the problem he'd been assigned. Tropical tire durability had been achieved through systematic application of chemical principles. But Larsen also understood the larger context. His work on antiozonants and antioxidants was applicable far beyond military tires. After the war, the formulations Larsen developed would become standard throughout the rubber industry. Every tire produced in the subsequent decades would incorporate some version of the protective systems he pioneered. The 6 ppd he selected would remain the industry-standard antiozonant into the 21st century. The carbon black grades he specified would define reinforcement protocols across countless applications, but in November 1943, those future applications remained invisible. The immediate concern was producing enough tires to meet military requirements while simultaneously solving the broader rubber crisis. Because tire compounds, no matter how improved, were worthless without sufficient rubber to compound. The synthetic rubber program had expanded dramatically since March 1942. Firestone, Goodyear, Goodrich, and United States Rubber had constructed or expanded 51 production facilities across the United States. These plants converted petroleum feedstocks and grain alcohol into butadiene and styrene, polymerized those monomers into GRS rubber, and processed the resulting material into bales, ready for compounding. Production numbers told the story. In 1942, the 4 major companies produced 2,241 tons of synthetic rubber. By 1944, that figure had exploded to 495,000 tons, and by 1945, American synthetic rubber production exceeded 900,000 tons annually, representing 85% of total rubber consumption. This was not simply an industrial achievement. It was a chemical revolution accomplished under war conditions, with deadlines measured in weeks rather than years, with quality requirements that demanded perfection despite unprecedented production rates. The scale of the transformation becomes clear when compared to peacetime industrial development. A typical chemical plant required 5 to 7 years, from conception to full operation. The synthetic rubber program compressed that timeline to less than 18 months. The human cost of this acceleration rarely appeared in official reports. Engineers worked 80-hour weeks. Chemists slept in their laboratories. Production workers handled toxic chemicals with inadequate safety equipment because proper protective gear wasn't available. Polymerization vessels exploded during startups. Solvent leaks caused fires. Rushed. Construction left structural weaknesses that led to equipment failures. But the alternative was losing the war. And that reality justified risks that would have been unconscionable under peacetime conditions. Bill Larson visited several production facilities in early 1944, observing how his laboratory formulations translated into industrial-scale manufacturing. The compounding process fascinated him. Giant Banbury mixers, heated to 270 degrees Fahrenheit, churned polymer, carbon black, and processing chemicals into homogeneous masses that emerged as sheets of uncured rubber. These sheets fed into extruders that formed the basic shapes, treads, sidewalls, bead cores that would be assembled into finished tires. The vulcanization process occurred in massive presses that heated the assembled tire to 300 degrees Fahrenheit under precise pressure profiles. Sulfur bridges formed between polymer chains, creating the three-dimensional network that gave cured rubber its elasticity and strength. The chemistry was complex, involving reactions between sulfur, accelerators, activators, and the double bonds in the polymer chains, all occurring simultaneously in a material that was heterogeneous on the microscopic scale. Quality control represented another challenge entirely. Each tire needed to meet specifications for dimensions, balance, uniformity, and strength. Testing protocols included X-ray inspection for internal defects, dynamic balancing to detect asymmetries, and destructive testing of sample units to verify that material properties matched requirements. Larson observed one destructive test that crystallized the stakes involved. A tire, randomly selected from production, was mounted on a test drum and run at 70 miles per hour until failure. The specification required minimum performance of 12,000 miles. The tire lasted 14,300 miles before tread wear exceeded acceptable limits. That tire, and the millions like it, represented the difference between mobility and paralysis for American forces operating across the Pacific. But Larson's most significant realization came not from watching production, but from talking to the workers who operated the machinery. These weren't PhD, chemists or engineers with advanced degrees. They were men and women, many with only high school education, who understood the equipment through experience and intuition rather than theory. They could diagnose problems from subtle changes in sound or smell. They could adjust processing conditions to compensate for variations in raw materials. Their expertise was empirical rather than theoretical. But it was absolutely essential to maintaining production quality. One operator, a 47-year-old woman named Helen Morrison, explained her approach to compounding. The mixer tells you what it needs. If the batch is too dry, you hear it in the sound, too wet, and the discharge is sloppy. The temperature profile during mixing affects everything downstream. I've been running this Banbury for 18 months, and I can feel when something's not right. The engineers have their instruments, but sometimes you just know. Larson recognized that Morrison's intuitive understanding complemented his theoretical knowledge. The best formulations emerged from combining both approaches, from letting practical experience inform theoretical predictions, from testing laboratory hypotheses against production realities. By mid-1944, the rubber crisis that had threatened American war production had been comprehensively solved. Synthetic rubber production exceeded military requirements. Tire durability had been dramatically improved through better compounding. The supply chain that had collapsed with the fall of Singapore had been replaced by domestic manufacturing that was immune to enemy interdiction. But solving the immediate crisis revealed longer-term challenges. Synthetic rubber was more expensive than natural rubber. The quality, while adequate for military applications, didn't match natural rubber's performance in many civilian uses. And the environmental impact of large-scale synthetic rubber production was becoming increasingly apparent. The polymerization process generated substantial waste streams. Unreacted monomers had to be recovered or disposed of safely. Soap emulsifiers contaminated process water. Carbon disulfide used in some formulations was toxic and difficult to handle. These problems weren't critical during wartime, but they would require attention as the industry transitioned to peacetime operations. Larsen began thinking about these challenges in late 1944, even as the war in Europe approached its conclusion. He understood that synthetic rubber wouldn't disappear after the war ended. The production capacity existed, the technical knowledge had been developed. The market for rubber products would continue growing as automobile ownership expanded and industrial applications multiplied. The question was, how to improve synthetic rubber to the point where it could compete with natural rubber on quality and cost, rather than merely serving as an emergency substitute. That required better polymerization control, improved monomer purity, optimized compounding formulations, and more efficient production processes. In January 1945, Larsen submitted a research proposal to Firestone's technical committee, outlining a program to develop next-generation synthetic rubber. His proposal focused on cold polymerization, a process that had been developed in Germany but not yet implemented in American production. Cold polymerization occurred at 5 degrees Celsius rather than the 50 degrees used in hot polymerization, producing longer polymer chains with more uniform molecular weights. The technical committee approved the proposal, and Larsen began assembling a team to investigate cold polymerization in April 1945. The timing was fortuitous. Germany surrendered in May, and American technical intelligence teams immediately began documenting German chemical processes. The reports they filed included detailed information about IG Farben's cold polymerization methods, information that would have taken years to develop independently. Larsen received these technical intelligence reports in June 1945 and realized that German chemists had solved many of the problems that plagued American synthetic rubber production. Their cold polymerization process produced rubber with properties that closely approached natural rubber. Their compounding formulations achieved better heat resistance and lower temperature performance. Their production methods generated less waste and used fewer toxic chemicals. The challenge was adapting German methods to American equipment and raw materials. German plants used different emulsifiers, different initiators, different reactor designs. Simply copying their procedures wouldn't work. Understanding the underlying chemistry and translating it into American production systems required careful experimentation and substantial investment. Firestone committed to that investment in July 1945. A new research facility was constructed specifically for cold polymerization studies. Larsen recruited chemists and engineers from other divisions. Equipment was purchased or custom-built to match German specifications. By September 1945, the team was conducting pilot-scale polymerization runs. The results exceeded expectations. Cold polymerized GRS rubber showed improved resilience, better low-temperature properties, and superior resistance to crack growth compared to hot polymerized material. Tires made from cold GRS matched natural rubber performance in almost every category, and the production process, while more complex than hot polymerization, was economically viable at industrial scale. Commercial production of cold GRS rubber began in 1948, 3 years after the war ended. By 1955, when the government sold its synthetic rubber plants back to private industry, cold polymerization had become the standard method. The wartime emergency program had evolved into a permanent industry that would eventually produce more synthetic rubber than the world had ever consumed of natural rubber. Bill Larsen continued working at Firestone until his retirement in 1976. He held 43 patents, most related to rubber compounding and polymer chemistry. He trained 2 generations of chemists who went on to lead research programs throughout the rubber industry. He published extensively in technical journals, contributing to the scientific understanding of polymer degradation mechanisms and protective chemistry. But his most significant contribution remained the work he did in 1942 and 43, solving the tropical tire durability crisis that threatened to ground American military vehicles across the Pacific theater. That work didn't make headlines. It didn't generate dramatic battlefield victories. It was unglamorous chemistry, mixing antiozonants and antioxidants and carbon blacks into rubber compounds that simply worked the way they were supposed to work. Master Sergeant Mike Quirk never met Bill Larson. He never knew the name of the chemist whose formulations kept his jeeps mobile through the Solomon Islands campaign. But in August 1945, when Japanese forces surrendered and Quirk found himself with time to write letters, he composed one to the Firestone Tire and Rubber Company. "I'm just a mechanic," Quirk wrote. "I don't understand chemistry or laboratories or how rubber gets made. But I know that about a year ago, the tires we were getting changed. They stopped falling apart in the jungle. They lasted long enough to actually wear out from use instead of just rotting away. I don't know who figured that out, but I want them to know it mattered. A lot of Marines are alive because their supply trucks could still move. A lot of wounded made it to hospitals because ambulance jeeps had functional tires. That's not the kind of thing that gets reported in newspapers, but it's the kind of thing that wins wars." The letter reached Firestone's headquarters in September 1945 and was eventually forwarded to the research division. Larson received it in October, read it twice, and filed it in his desk drawer. Years later, after his retirement, he would tell an interviewer that Quirk's letter meant more to him than any of the professional recognition he'd received. "We were just doing our jobs," Larson said in a 1981 interview. "The military had a problem. Rubber was failing in tropical conditions. We investigated the chemistry, identified the degradation mechanisms, formulated protective additives, and tested them until they worked. That's what chemists do. That's what engineering is about. You find problems and you solve them, not because it's exciting or glamorous, but because people need things to work properly." The synthetic rubber program that emerged from World War II became one of the foundational achievements of modern chemical engineering. It demonstrated that industrial-scale problems could be solved through systematic application of scientific principles. It proved that competing companies could cooperate when national survival demanded it. It established quality control procedures and testing protocols that would define manufacturing standards for decades. But at its core, the program succeeded because individuals like Bill Larson understood that chemistry wasn't abstract theory. It was molecular reality with practical consequences. It was double bonds that reacted with ozone. It was free radicals that propagated through polymer chains. It was carbon black particles that reinforced rubber, matrices. And it was antiozonants and antioxidants that protected all of that chemistry from tropical environments that would otherwise tear it apart. The tires Larson formulated in 1943 are long gone, worn out and discarded 70 years ago. The jeeps they carried have been scrapped or preserved in museums. The Marines who depended on them have mostly passed away. But the chemistry Larson pioneered continues. Every tire manufactured today incorporates descendants of the protective systems he developed. Every rubber product that resists ozone and heat and oxidation does so using principles he helped establish. In the end, that's the real measure of scientific achievement. Not publications or patents or professional recognition, but whether the work matters beyond the laboratory, whether it solves real problems for real people, whether it makes things work better than they worked before. Bill Larson made tires last 12,000 miles in jungles that should have destroyed them in 600 miles. He did it with chemistry that most people never see, protecting rubber with molecules that most people have never heard of. It wasn't dramatic, it wasn't glamorous, but it was absolutely essential. And sometimes, the unglamorous chemistry that keeps things working is exactly the kind of achievement that changes everything. The final irony emerged decades later, as environmental historians began studying World War II's industrial legacy. The synthetic rubber program, conceived as an emergency measure to replace natural rubber supplies cut off by enemy action, had inadvertently created an industry that would eventually dwarf natural rubber production. By the 1980s, global synthetic rubber production exceeded 1 million tons annually, far surpassing the natural rubber output that had seemed so irreplaceable in 1941. This shift had profound consequences. It reduced dependence on tropical agriculture, limiting the economic power of rubber-producing nations. It enabled new applications that natural rubber couldn't satisfy, particularly in aerospace and automotive engineering, where precise property control mattered more than simple availability. And it demonstrated that natural materials, no matter how perfectly evolved for their biological functions, could be matched or exceeded by rational design based on chemical principles. But the shift also raised questions about sustainability. Synthetic rubber came from petroleum, a finite resource. Natural rubber came from trees, a renewable resource if properly managed. The environmental cost of synthetic rubber production, including energy consumption and waste generation, exceeded natural rubber's impact. These trade-offs became increasingly important as global rubber consumption continued growing. Modern rubber chemists continue building on foundations established during World War II. They develop new antiozonants with improved performance. They optimize carbon black formulations for specific applications. They create novel cross-linking systems that extend service life. And they work to reduce environmental impact, developing bio-based rubbers and more sustainable production processes. Bill Larson's contribution remains embedded in this ongoing work, often invisibly, as the principles he helped establish have become so fundamental that they're rarely attributed to any individual. The aromatic amines that protect against ozone, the phenolic antioxidants that prevent thermal degradation, the carbon black grades that provide reinforcement. These are simply how rubber is formulated, the standard practice that every chemist learns. But standard practice once was radical innovation, accomplished under deadline pressure by someone willing to challenge established assumptions. The tires that lasted 500 miles weren't failing because of fundamental limitations in rubber chemistry. They were failing because nobody had systematically addressed the specific degradation mechanisms operating in tropical environments. Larson addressed those mechanisms, not through dramatic breakthroughs or revolutionary insights, but through careful analysis, systematic experimentation, and persistent optimization. It was professional competence applied to a critical problem, producing results that saved lives and enabled military operations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.